Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to the 5 most commonly missed AP questions, Limit Edition. Our first most commonly missed question is this tame looking limit. The limit as x approaches 3 of the absolute value of x minus 3 over x minus 3. There's a couple different ways to approach it. We're going to look at algebraically first, and we should definitely try to plug in 3 to our limit first and foremost. But as you can see, we're clearly going to get a 0 on the top and a 0 on the bottom, which is one of the most common outcomes we'll run into, which means we have to analyze this another way. So let's handle this absolute value algebraically. The way to do that is to split the absolute value into 2 different cases, the positive case and the negative case. So if we take a look at this limit as x approaches 3 from the right, strictly of values of x that are greater than 3, if we plug in those values that are greater than 3 into the absolute value expression, it's always going to be positive up there, and the denominator is always going to be positive. So there's no need for the absolute value to take any effect, so we can essentially just get rid of it, making our limit just x minus 3 over x minus 3. Here, we can simplify these two out of the way, leaving us with just a positive 1. If we check the limit coming from the other direction, the limit as x approaches 3 from the left, we can tell that when we try to plug values of x in that are slightly less than 3, when we do that to the absolute value expression, 2 minus 3 is going to be negative 1, but the absolute value is going to turn it positive. So any value of x that's less than 3 is going to make that numerator expression negative, but the absolute value expression has to flip it to positive. So how do we do that? We multiply that whole expression by a negative, and that's going to turn the negative value into a positive. Everything else stays the same. So again, we can cancel out these x minus 3 pieces, and this time we just get negative 1. Now it's pretty clear that these two-sided limits do not equal each other, and that gives us our answer to the original question. The limit as x approaches 3 has to take into account both of these points of view, and since they don't equal to each other, the overall limit is not going to exist. That'd be the algebraic way to approach this. Personally, I prefer to think about this graphically. The concept is very similar. When we try to plug in values as x approaches 3 to the numerator and denominator, we have to consider the right and the left values. If I pick values that are strictly greater than 3 and I try to plug them into this expression, 4 minus 3 is going to be 1 over 1. 5 minus 3 is going to be 2 over 2. 6 minus 3 is going to be 3 over 3. All of these fractions reduce to 1. So it becomes pretty clear that if you try to plug in any value greater than 3 to this expression, you're going to end up with 1. Graphically, that's just going to be a horizontal line at y equals 1 for everything to the right of 3. It's still definitely undefined when x equals 3, so we'll put an open circle there, but just that horizontal line. Same story when I try to plug in values of x that are less than 3. I'm going to end up, the numerator will always be positive, but when I plug in something less than 3 in the bottom, I'm going to end up with negative. They're going to cancel out, reduce down to negative 1. So I'm just going to get a horizontal line going to the left and negative 1. And you can see, because we have this jump in our function around x equals 3, that our limit definitely does not exist. Our second most commonly missed limit question on the AP test is this little guy. The limit as x approaches 0 of sine of 5 of x over 3x, or something similar. To answer this question, they're banking on you utilizing one specific fact. And that's this special limit. The limit as u approaches 0 of sine of u over u is equal to 1. Now I use u for a reason. I don't want you to get confused with x. The only reason I put it in there is because whatever expression is in your sine function, as long as it matches what's in the denominator, this limit is going to equal 1. We just need those two things to match up. And you can see in our problem that we have 5x in the sine function, 3x in the denominator. Those don't match. So we have to somehow make this limit match so we can use this special limit to our advantage. How do we do it? Well, we'd like a 5x on the bottom, so let's just make it a 5x. Let's multiply the numerator and denominator by 5, rewriting the limit. Well, the limit as x approaches 0 of 5 sine of 5x. And instead of multiplying those denominators together and getting 15x, I'm just going to keep it as 3 times 5x, writing it specifically so I have that numerator and denominator match. Then we can pull out the coefficients of 5/3, rewrite our limit to the limit as x approaches 0, bring the 5/3 out front. We just have sine of 5x over 5x. This matches our special limit, so we're just going to get 5/3 times 1, which is obviously just 5/3. That'll be our answer to this question that is commonly missed. Right? Shortcut alert. Right? This question is asked pretty frequently, and almost always the answer is just the coefficients. No matter what algebra you do, I always used to just think, well, it's probably going to be 5/3, and then lo and behold, with whatever magic algebra you throw in there, it ends up being 5/3. So if you wanted to just guess on this problem, it'd be a pretty safe guess to guess the coefficients. Our next most commonly missed limit is something like this. The limit as x approaches 2 of x squared minus 4 over x squared minus 4x plus 4. Again, looks pretty tame, like something that you would have seen that seems easy. When you try to plug in 2, you are going to get 0 over 0. So that says, hey, go back and analyze this. Let's see if we can simplify it. And definitely looks factorable, so I think we'll start there. And what do we get? The limit as x approaches 2, the top factors into x plus 2 times x minus 2. Our denominator will give us 2 factors of x minus 2. And yeah, we can cancel this out, leaving us with the limit as x approaches 2 of just x plus 2 over x minus 2. But now when we try to plug 2 into this, we're going to get 4 over 0. And we don't want to make any assumptions here. That's what lots of students do. When you get a number over 0 that's not 0 over 0, we want to acknowledge that this means our function has a vertical asymptote at this point. What we don't know is if our function is going to be going up the vertical asymptote or down it. So we do have to check both sides to see what happens. I have to check the limit as x approaches 2 from the left of x plus 2 over x minus 2, and the limit as x approaches 2 from the right of x plus 2 over x minus 2. Since we know there's a vertical asymptote, we know the answers can only be positive infinity or negative infinity. So when I check values of x that are a little bit less than 2, I only care if my answer is going to be positive or negative. And when I plug in something slightly less than 2 to the numerator, I'm going to get a positive value. But when I plug in like 1.9 to the denominator, I'm going to get a negative value. So this is always going to result in a positive divided by a negative as I approach this vertical asymptote from the left, which means my function values are always going to be negative, and this limit is going to approach negative infinity. Playing the same game with this bottom limit, as we approach 2 from the right, so values that are slightly greater than 2. Certainly when I plug that into the numerator, I'm going to get a positive. And if I plug in 2.1, 2.2, 2.2 minus 2 is still going to be positive. So overall, my function is going to be positive, and this limit's going to approach positive infinity as we get closer to our vertical asymptote. Now, since we see that these two limits don't approach the same value, we can answer our original limit and confidently say that this limit does not exist. Now, if any of our questions specifically ask just about the left or the right, they would exist. The left approached negative infinity, and the right approached positive infinity. On to our fourth most commonly missed limit type question on the AP exam. The limit as x approaches negative infinity of radical 9x to the 6th plus 3x minus 1 over 2x cubed minus 5x squared plus 4. All right, now you might be familiar with this type of question, a limit as x approaches infinity or negative infinity. This is definitely asking us about the end behavior of our function. And when we think end behavior, we definitely want to contemplate horizontal asymptotes. Now, hopefully you recall when we're analyzing this for horizontal asymptotes and end behavior, we want to check the degree of the numerator versus the degree of the denominator. And right now it says x to the 6th over x to the 3rd, but you got to be careful because that radical is affecting that x to the 6th. So if we actually take the square root of that first term, we don't really care about the other terms. We only care about what the highest power is going to be. So I'm just going to isolate the first term and take the square root of that and say, well, our limit is really approximately going to look like the limit as x approaches negative infinity of 3x cubed plus some other stuff over 2x cubed plus some other stuff. Again, we don't really care about that other stuff, but now we can see that definitely the powers match up, so the numerator and denominator are growing at the same rate, and hopefully you remember that when this happens, we look to the coefficients to tell us what this limit's going to be. So most students will say that the answer to this question is 3 over 2 through a pretty thorough and accurate analysis. However, this is actually wrong. The error comes in underestimating what the negative is doing to this problem. If we only assess what's happening in our simplified version after we took the square root of the numerator, what's happening when I plug in this negative, certainly when I plug in negative values and I cube them to the numerator, it's going to be negative. When I cube them in the denominator, they're going to be negative. So these two negatives would theoretically cancel each other out, leaving us with a positive 3 over 2. The issue is the original problem has this x to the 6th that's in the square root. So when we plug in a negative, it's first going to be raised to an even power, that power of 6, which is going to turn that negative positive. Then we take the radical of it. The radical of a positive number is going to stay positive. So the whole numerator will be positive. The denominator will stay negative. So we are going to have a positive over a negative in this specific instance, and that's super easy to miss. Now, all the other analysis still holds. The powers are going to be the same. They are going to essentially grow at the same rate, but we just have to acknowledge that the end result is definitely going to be negative. Thus, we conclude the limit that we started with doesn't go to 3 over 2. It actually goes to negative 3 over 2. And this is very commonly missed. Okay? Especially because if I ask this question a different way and I started as the limit as x approaches positive infinity, we would have no issues. Your original logic would have been completely fine, and the answer will be positive 3 over 2. And it's super uncommon to have a horizontal asymptote on the right, which is different than a horizontal asymptote on the left. That's why this is commonly missed. Which brings us to our last most commonly missed type of limit question on the AP test. Right, here we have two graphs, f of x and g of x, and I'm going to ask something seemingly simple, the limit as x approaches 1 from the right of the function composition f of g of x. Now, when we begin to assess this, we have to be extra careful. We are taking the limit as x approaches 1 from the right. We're going to start on the inside function, definitely g of x. So we're going to see what g is doing as we approach 1 from the right. Now, certainly we can see that we're approaching a y value of negative 1. But extra emphasis here, we're approaching that y value of negative 1 from values that are less than negative 1, which means we're approaching negative 1 from values below negative 1, so we're actually approaching negative 1 from the left, which is kind of confusing and hard to see. So pause the video if you need to make sure you see exactly why we're approaching negative 1 from below or from the left. Which means we can rewrite this limit as the limit as x approaches negative 1 from the left of just f of x. So we've already passed the part where the common mistake is made, and now this is a pretty easy, straightforward question. We're going to look at the graph of f, where x equals negative 1, and we're going to approach that from the left. Looking at the left part of this graph, it looks like we're approaching a y value of 4. Now let's take a look at the common mistakes here. If you would have assessed this first part and just said you were approaching negative 1 and didn't notice you were approaching it from the left, then you would have looked at your f of x function from both sides, and you would have noticed that they were going to different places, and you might have mistakenly said that this limit does not exist. So it's extra important that you notice the first function, we're approaching negative 1 from the left. So we just look at the left side and determine that the answer is 4. Now, how would I change this problem to get you to look at the right side? I'd have to change the way that my g of x function is drawn. So if I erase my g of x function just to the right, and instead of going down after that point, I go up, now as I approach 1 from the right, I'm still approaching a y value of -1. But if we take a look at our graph, we're approaching that y value of -1 from values of y that are larger than 1. We're going up, so the y values are above 1, which means we're approaching 1 from the right, which would change our secondary question here to the limit as x approaches -1 from the right, which is going to affect where we look on our f of x function. We're going to look at the right piece, which is definitely going down towards -2. So very subtle changes in the graph can affect your answer to this question, and that's why it's commonly missed. Now, I hope you found this guide helpful to the 5 most commonly missed questions limit edition. We'll post other editions, derivatives, antiderivatives, with commonly missed questions in the future. Be sure to check out our other videos as well that'll walk you through every section of the AP Calculus curriculum. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.